All right, 5.2, the addition rule and complements. All right, two events are disjoint if they have no outcomes in common. Another name for disjoint is mutually exclusive. So we use those two terminologies um, together there with that, okay? So disjoint means there's nothing in common. So we can see that in this Venn diagram here. We have the two circles. Notice that the things in the circles are completely different from each other, so they don't have anything in common. They don't overlap when we're doing those pieces, okay? And so we would call these disjoint because they have nothing in common. All right, so if we were going to look at the probability of event E there, so picking something out of E, then we would add up those numbers. So we have three of those things within that piece there. So 3 out of 10 would give us 30% or 0.3. And then the probability of picking something out of F, we have 2 in there. So 2 out of 10 is 0.2. Now, what about the probability of picking something that's in either E or F? Well, there are 5 items there, and so 5 out of 10 would give us 0.5. Now, there is another way of doing it. Because they're disjoint, we could just have taken the two original probabilities, P of E, probability of E, and probability of F, and added them together, and we still get the same number, okay? And so that is what our first rule is here. So for disjoint events, they must be disjoint or mutually exclusive, that the probability of E or F happening is the probability of E plus the probability of F. Okay? And we can extend that to more than 2 events. We can have a multitude there with them, as many as events that we need to have happening on those. Okay? And so here's an example of that. So again, we can find the probabilities of each of the individuals, add those things together with those pieces, as long as they're disjoint for that. And so the probability of E or F or G is 0.7 here. Okay. All right, so here's another example looking at this. So we have our number system, 0 to 9. Now, if we're going to actually write a digit, we never start with a 0. And so the probability of the first significant digit is only 1 out of 9. Okay? Now, Simon Newcomb discovered that these typically don't happen with frequency when people are doing these. And so he came up with this table here of probabilities that the first digit will be one of these numbers, 1 through 9, when we're looking at it, okay, for those. And so we first check and make sure it's a probability model, and it does satisfy those things. All our numbers are between 0 and 1. They all add up to 1 with that, okay? And so what is the probability based on his table of randomly selecting a number where the first digit is a 1 or 2? Well, if we go back to the table, the probability of 1 is a 0.30. The probability of his 2 is a 0.176. And so we add those together to get 0.477 for those. Okay, so we would expect about 48 numbers out of 100 to begin with 1 or 2 when we're creating those numbers. Now, what about the probability of the first digit being at least 6? So that means it has to be a 6, 7, 8, or 9. And so if we add up those probabilities, we get 0.222 there with those. Okay? And so we'd expect out of 100 numbers, 22 of them to begin with a 6, 7, 8, or 9. All right, another example here, looking at a deck of cards. And so this is what our deck of cards looks like with that. If we've never played cards before. Most of us have, though. But we have 52 cards in the deck, all going from ace to king on those. We have spades, hearts, clubs, and diamonds on those. All right, so we want to compute the probability of drawing a king. All right, so we know there are 52 cards, and 4 of those cards are kings. So therefore, it's 4 out of 52, or 1 over 13. And again, we could just plug that in our calculator and get that division for a decimal. Now, what is the probability of drawing a king, or a queen, or a jack? Okay, so these things are mutually exclusive, and so we would look at each one of those. So we would have 4 out of 52 for each one of those. We add that together and reduce, and we get 3 out of 13 for those. Okay. Now, what about the general addition rule? That means what if we have an overlap? They're not disjoint. Okay? So we need to take things into account. Now, we're just looking at computing it directly and counting the things. We can see that there are 8 items in the circles. So we're looking at whether it's in E or F here. We've counted up all those items. There are 8 different items in the circles out of the 10. And so 8 out of 10 means that it reduces to 4 out of 5 with those, or 80.8 if we were to do that math. Okay. Now, if we were to actually do our old rule, we would see that that gives us 1, and that's not true with those. And so we have to take things into account. Now, it's not always going to equal 1, but it's not going to equal the right thing either. So our rule here is that we have to think about the overlap. Because we're counting that overlap twice, we need to subtract off one of those things. And so our new rule here is going to be the probability of E plus the probability of F minus the overlap, which is the probability of E and F on those. Okay, and so there were 5 things in the E circle, there were 5 things in the F circle, and there were 2 things that overlapped, so we needed to subtract that off to get our 8 out of 10 for those pieces. Okay, and so that is going to be our addition rule for those. Now we could actually use this all the time because if they don't overlap, the P of E and F would be 0, and so we would subtract off 0 for those pieces, and that's what makes it disjoint on those. But if it's not disjoint, we have to subtract off that piece. Okay, so let's look at here. We want to compute the probability of drawing a king or drawing a diamond. Okay, so we have the probability of a king plus the probability of a diamond minus the king of diamonds because we don't want to count it twice. We've already counted it with the king, and we're counting it again with the diamonds, so we don't want to count it twice. That's why we're subtracting it off for those pieces. And so for a king, there's 4 out of 32. For a diamond, there's 13 out of 52. And then the king of diamonds, there's 1 of those. So it gives us 16 out of 52 that reduces. Okay. All right, so we see that there. So for 4 out of 13 for our final. All right, so the next few examples, we want to look at these table. This table is called the contingency table, or a two-way table, because it has 2 categories of data with those. Okay, we talk about males and females, and then breaking those things down into never married, married, widowed, divorced, and separated. So we can do those different types of things for that. Okay, and so the row is our variable is marital status, and the column, our variable, is gender on those pieces. Okay. All right, so we want to be able to answer some of these questions. So one, what is the probability that we select a male? What is the probability that that we select a widowed? What is the probability of being widowed or divorced? And then what is the probability that they are male or widowed? So we need to pay attention to all those things. So the first thing is we really need to know the total amount. And so we know the males, we can add those up with those. But the total amount is we need to add everything from those pieces down there. And so we add those all together, we get 260.1 million residents there for those. If we add all the columns, all the numbers in the table, we'll get that piece, okay, for that. All right, and so the males there, the total amount of males we said are 126.9, and so we would divide that by the 260.1 to come up with 0.488. So 48%, almost 49% on this table are males. Okay. Now, what about widowed? Now, we're still out of the total amount. And so we have 15.2 that are widowed. Now, if we go back here, we got to be careful. We can see that widowed is these 2. Okay. So we got to add those things together for those. So making sure we're paying attention to those items. So that is where they come up with the 15.2 is by adding those pieces. All right, and so out of the total amount. Likewise here, widowed and divorced. Well, these things are disjoint and so we can just add them together. Now again, we gotta get our total widowed, total divorced, and add those out of the total amount there before we divide. Okay. But when we look at our last one, male and widowed, these are not mutually exclusive. And so we need to use the general rule. And so we need the probability of male plus the probability of widowed minus male and widowed for that. So we look there, the male we had added together and we got 126.9. The widowed was 15.2. We go back to our table though where it says male and widowed, we have 3.3. And so we need to subtract that one off for that, okay? And so that would give us 0.534 after we do that math. All right, complement. The complement of an event is the outcomes that are not going to happen. So instead of looking at E, we want the things that are not E with those, okay? And so we denote that with a C superscript there with those. So we're going to be looking for that. All right, and we can find those things by doing 1 minus the probability of E with that. So that's going to be our formula there for the complement. Okay, and so we can see this. E is what's in the green circle. The complement of E is anything outside of it, whether it's in the white area, whether it's in another circle, any of those types of things. Those are the complement of E for them. All right, so here, we're looking at a gambling study. It says 52% of Americans have played state lotteries. What is the probability they have not played? And so we do the 1 minus the played, and we get 48%, or 0.48, have not played. Okay, so we can do that subtraction. 1 minus is the opposite. Okay. All right, so the next ones look at our income. So annual income being all these things and the number of people within those. Okay, so we want to be able to answer some questions from this table. So the first, find the probability that somebody earned more than $200,000. Okay, so if we go back here and look at that, we could add all of our numbers in thousands there together, and then we do 8,284 divided by that number. Okay, and so that's what they did there. There were 120,000 people here that were surveyed, and so we have a final answer of 0.069 when we're looking at that. Okay, and so again, out of 1,000 people, we'd expect 69 of them to have an income of more than $200,000. Okay, now what about less than $200,000? Well, instead of going back and adding all the other numbers, we can just simply subtract because we know how many people made 200,000 or more, and so we just do 1 minus that because it's its complement. That's what the less than means there with that. Okay, so we could just subtract that off, and we would expect 0.931 with those. So 93% of the households earn less than $200,000. Okay. Now, what about at least? We can do that as well. We know when we go back to the table that there were 7,804 households that earned less than $10,000. And so we can do the complement there with that one to get at least, because at least is greater than or equal to. And so we do that subtraction as well for those. Okay. And so that would give us our expectation. So 93%, almost 94%, make at least $10,000. All right. All right, so those are the formulas and things that you're going to need there for 5.2.